to present our joint research entitled Modeling of Shape Memory Alloys Hysteretic Behavior Considering the Loading Cycles Frequency. Shape memory alloys are unique materials that can restore their previous shape under certain conditions such as temperature changes or mechanical stress. These properties allow shape memory alloys to be used in many fields, for instance in aerospace, construction and medicine. In our work we studied the properties of shape memory alloys based on nickel and titanium alloy, namely the effect of superelasticity. Machine learning is one of the key technologies that is increasingly being implemented in various fields of science and technology due to its ability to automate processes, analyze large amounts of data, and make highly accurate predictions. In material science, machine learning allows us to predict the properties of materials. Particularly, machine learning minimizes the need for expensive and time-consuming experiments. The main goal of our study is to create models capable of accurately predicting hysteresis loops for different frequencies, taking into account the complexity of processes occurring during the formation phase transformations. A neural information processing unit is fundamental to the function of a neural network. The diagram in the figure shows a model of a neuron that serves as the basis for a neural network. To train the artificial neural network, we used experimentally obtained hysteresis loops for 4 loading frequencies of 0.1, 0.51, and 5 Hz. The input data consisted of the following parameters: thrust sigma, NMPA, cycle number n, and loading frequency f in Hz. When analyzing these functional dependencies, the neural network learned to recognize patterns which allowed it to predict the strain at different loading frequencies. To train the multi-layer perceptual neural network, we use data from 1020 loading cycles of shape memory alloy materials. The dataset for the loading period up direction contained roughly 3,500 elements. The dataset was divided into 3 unequal parts. 80% of the data was randomly selected for model training, 10% of the data was selected for model validation during the training process to control overfitting, and another 10% was selected for testing to evaluate the quality of model prediction of new data. For the loading period down direction, we used around 3,400 elements, which were distributed in the same way. In this paper, the following forecasting error metrics were used to evaluate the model's performance: mean absolute error MAIA, mean squared error MSE, and mean squared error RMSE, and mean absolute percentage error MAPE. The figures on the slide shows the dependencies between the experimental determined and predicted material strain A test true and A test predicted respectively. As you can see, the data are very close to the bisector of the first coordinate angle, which confirms the high accuracy of prediction. The table shows the prediction errors for the loading and unloading stages for the multi-layer perceptual neural network model of shape memory alloys hysteretic behavior for 4 frequencies. So in this table you can see various prediction errors, and they are quite low, which confirms quite good forecasting results. Figure shows the dependencies between the experimental values of material strain and the predicted values obtained during model testing on the 1025th loading and unloading cycle at a frequency of 0.1, 0.51, and 5 Hz. As you can see from the slide, the prediction is quite accurate. Table shows the values of the prediction errors for the loading and unloading stages of the simulation of the hysteretic behavior of the nickel titanium alloy for 1025 cycles and 4 frequencies. Figures shows the hysteresis loop for 1025 loading and unloading cycles constructed using artificial neural network and the corresponding experimental data at the frequency of 0.1 Hz and 0.5 Hz. As you can see from these plots, the simulation results are quite accurate. On this slide, figure shows the hysteresis loop for 1025th loading and unloading cycle constructed using artificial neural network and the corresponding experimental data and the frequency of 1 Hz and 5 Hz. As in the previous results, the predictions results are quite good. Conclusions. The obtained results showed that the multi-layer perceptron model can predict the material strain absolutely with high accuracy depending on the applied stress sigma, cycle number n, and loading cycle frequency f. The low values of the prediction errors such as mean average error, RMSE, and MAPEC confirm the high accuracy of the model during both the loading and unloading stages. Importantly, the model confirmed its ability to accurately predict the material behavior for a cycle it had not seen during training. This indicates the model's ability to generalize and adequately predict material behavior under different loading conditions.